Hello everyone. Let's start with a simple question. Are you in motion right now or at rest? If you're sitting on a chair, you might say you are at rest. But think again, with respect to the spinning earth, you're actually moving at nearly 1600 kilometers per hour. This simple thought reveals something very profound in physics. Motion and rest are not absolute, they are always relative to something else. For example, a car speeding on the road or a bird flying in the air are clearly in motion, while a book lying on a desk is at rest because its position relative to the desk does not change with time. Now, let's go a little deeper. Imagine a person sitting in a boat moving across a river. With respect to the boat, the person is at rest because their position inside the boat is unchanged. But with respect to the river bank, the same person is in motion. Similarly, two cars going side by side with the same speed appear at rest with respect to each other, but both are in motion with respect to trees and people standing on the roadside. This shows us that motion and rest are relative concepts. They depend on the observer's frame of reference, not on the object alone. To properly describe motion, we need to talk about the position of an object. In physics, we specify the position using three coordinates, x, y, and z. If even one of these coordinates changes with time, the object is in motion. We represent this using the position vector r equals x into I cap plus y into j cap plus z into k cap. For example, a ball falling freely under gravity shows a continuous change in its vertical coordinate y with respect to time. This mathematical language helps us describe motion precisely and universally.
Let's now classify types of motion. When only one coordinate changes with time, we say the motion is one-dimensional. Think of a train moving on a straight railway track, or a ball falling freely under gravity. Both are examples where the motion occurs along a single axis. Mathematically, we express it as x equals f of t. This means the position depends only on time along one line. Such motion is simple to analyze, yet forms the foundation for understanding more complex motion. Next comes two-dimensional motion, where two coordinates change with time. Classic examples include the motion of a planet around the sun, the circular motion of a stone tied to a string, or even an insect crawling diagonally on the floor. Here, the position vector is given by r of t equals x into I cap plus y into j cap. Projectile motion, like a ball thrown at an angle, is one of the most important real-life cases of two-dimensional motion. As you can see in the diagram, both the horizontal and vertical components change simultaneously, creating a curved path. Finally, we have three-dimensional motion where all three coordinates vary with time. Imagine a bird flying in the sky. Its x, y, and z positions keep changing together. Or think of a kite drifting in the wind, or even a gas molecule moving randomly in a container. In this case, the position is given by r of t equals x into I cap plus y into j cap plus z into k cap. Three-dimensional motion represents the most general and realistic case of motion that we encounter in the physical world. So let's bring everything together. An object is in motion if its position changes with respect to surroundings, and at rest if it does not. But remember, motion and rest are relative, not absolute. Depending on the frame of reference, the same object may appear at rest to one observer and in motion to another. Motion can further be classified as one-dimensional, two-dimensional, or three-dimensional, depending on how many coordinates change with time. These basic ideas are the foundation of kinematics and dynamics. From a cricket ball in play to the orbit of planets, everything begins with the concepts of motion and rest. I hope this session gave you clarity on how physicists define and classify motion. In our next lesson, we'll build upon this and explore how we measure motion mathematically using displacement, velocity, and acceleration. See you there.